Okay, thank you. Hi everyone, welcome to our virtual Lunch and Learn for September. It's great to see so many of you join us today. We do hope you enjoy today's topic. My name is Mark Foer. I'm a Client Engagement Principal and Machine Learning Practice Lead here at DiUS. And I have the pleasure of introducing today's talk on how computer vision can augment how we work and design new customer experiences. After a quick intro about DiUS, we'll be hearing from Nigel Hooke, our machine learning lead, and Shahin, Namin, machine learning engineer, on their experiences building commercial software applications powered by computer vision. They'll be sharing an overview of computer vision itself and some common applications, the solution landscape, and some challenges you might face on computer vision projects. They'll present two case studies, one in mining and the other in consumer insurance, that will touch on some of those challenges and how we overcame them. And then they'll share where they see computer vision going to next. Following the talk, there will be time to answer any questions you might have. We'll use Slido to capture those questions. So please go to www.sli.do and enter event code 91634. We'll also enter that into the chat screen. You can submit your questions during the presentation and they'll be read out and addressed at the end of the talk. Just to note that we do know there is quite a diverse audience here today, especially in terms of understanding and interest in the technical aspects of machine learning. Nigel and Shahin will touch on some technical concepts, but we'll keep it at a relatively high level. If you're curious about some of the deeper technical aspects or any other aspect for that matter that might not be addressed during the talk or Q&A, we'd be more than happy to get in touch and have a conversation with you outside today's session. Now, before I hand over to Nigel, a quick introduction to DiUS for those who don't know us. We're an Australian consulting company full of passionate technologists who love to build end-to-end solutions for and alongside our clients. We also build our own products. So the approaches we take and recommend are those that we have learned along our own journey. We're quite unique in that we have deep in-house expertise across digital, data and devices and how to bring it all together from experimentation right through to the rigor required for production. And we do all of this with a cross-functional approach and with experience design at the heart of it all, as you can see on the graphic on the right. This has meant that for the past 16 years since we've started, we've been fortunate enough to work across many industries and have been presented with many interesting problems and challenges that not only require our digital and cloud expertise, but also IoT and machine learning. Today's talk, however, is focused on machine learning, which is quite broad and a growing space that, as many of you already appreciate. At DiUS, we worked across a number of those application areas, including conversational AI, so chatbots and voice, natural language processing, recommendation systems, and of course, computer vision, which is our topic for today. So without much further ado, over to you, Nigel.
Thank you, Mark. So I'll be presenting an overview of computer vision, just so that you've got some idea of how it works and what's involved in putting together a solution. Next slide, please, Mark. So computer vision is just about applying machine learning to images and video. Nowadays, everyone has a smartphone with a camera that can take high quality images. And we also have access to improved machine learning algorithms with which businesses can process images to deliver value. And currently, computer vision is really the poster child of success for artificial intelligence. And I have some examples on the slide here, but essentially, computer vision can process images in a variety of ways depending on the desired outcome. So if your intent is to identify which objects are in an image, perhaps whereabouts they're located, how many there are, then you might use an object detection algorithm, and whether you're counting people or sheep, it's essentially the same algorithm doing both. You may want to be looking at a more complex image, such as a diagnostic scan of the brain. Shahin, looks like we've lost Mark there. Can you, if he doesn't pop up, can you grab the slide again, please? So if you have, say, a diagnostic image of the brain, you might be studying that, looking to find any areas with a particular kind of injury. And in that case, you'd use a technique called semantic segmentation, which just detects parts of the image. And here you can see a picture of a brain slice with some areas highlighted in green. Alternatively, if you want to know specifically which pixels form a particular instance of an image, and so in the lower right there, you can see a whole lot of people in a room, and the pixels for each person are colored a different color. That's another algorithm called instant segmentation, which is more and more being used these days. So there's quite a variety of algorithms we can use depending on what the objective is. Next slide, please. So we see two main ways that companies are adopting computer vision. The first is helping workers to do their work more efficiently. So every day in a pathology lab, microbiologists working there take hundreds of agar plates, such as that circular thing you can see on the image there. They take these culture plates out of the incubator and they assess them by eye to determine whether there's any growth on the plate that may be harmful to a patient. The majority of plates are negative and they just go in the toxic waste. The positive ones are set aside for further analysis. So you can have a machine that can do this with computer vision in under 10 seconds per plate. Basically, it photographs the plate, processes the image, separates the negative plates to put in the hazardous waste, writes a report, and moves the positive plates into a separate pile for further analysis. So this saves the microbiologist a lot of repetitive and somewhat boring work so that they can focus on the more challenging cases. And this is an example of how computer vision can augment the work that a human expert does and change the way that they work. The other way that we see computer vision being applied by businesses is in giving customers new experiences. Have you ever seen someone wearing some clothing or a fashion accessory and wondered where you could get one like it? In the retail space, there's a new startup called Trendy that lets consumers find where they can buy an item of clothing based on an image of it. So with the Trendy app, all you need to do is upload an image of what you're interested in, and it will find a matching or similar item in a retailer's catalog, letting you purchase it immediately. So this is a whole new customer experience that's powered by computer vision. Next slide, please. So when it comes to building computer vision applications, there's a spectrum of machine learning solutions that you can see here laid out from the left across to the right, with the easy to use general purpose techniques on the left and the more complex and highly specific on the right. So machine learning as a service on the left includes services from each of the major cloud providers, Azure, Google Cloud, and Amazon. These are easy for any programmer to use, but have limited capabilities and are only appropriate if your problem fits the narrow range of their capabilities. Moving to the right, we see services which can be customized to your needs, but require more skill to use. Further right, we have open source frameworks and deep neural network models that are even more powerful. DiUS works right across this spectrum, and we choose from the left if appropriate, but we also use technologies on the right if a more accurate or bespoke solution is required. Applying techniques from the right requires us to be aware of recently published research developments, which is a constantly changing landscape. For example, on the far right there, we have FixResNet and MobileNet v3, two new deep learning computer vision models that were announced in 2019. And we were using them on a customer problem soon after they were announced. Next slide, please. To give you some idea of how we apply these state-of-the-art models, so on the upper half of this slide, you can see a stylized breakdown of how a typical convolutional neural network deep learning model works for picking out objects in an image. So this is the kind of model which is trained on a large array of images of everyday objects, each one identified with the name of what kind of object it is. And the model basically processes each image when it's time for inference by passing it through these convolutional layers on the left and then through a number of fully connected layers at the trailing end, and finally, say, giving out a percent probability of which kind of object it can see in the image. And the way we would take one of these models and reuse it is essentially we take the convolutional neural network layers, we strip off the fully connected layers at the back end, and we replace that with some new neural network layers that are customized for the problem we're trying to solve. So for example, suppose we want to look at images of racing cyclists, and we want to isolate in each image which of the pixels represent a cyclist and which ones represent his bike. So essentially we would train a new model using the convolutional layers that we've taken from one of these pre-existing general purpose models. And now we just train those new layers that we've added on the back end, and we train it on images of the new kind of object that we want to detect. And that's typical of the approach that we use. Next slide, please. Thank you. So when doing a project with computer vision, there's a number of stages you go through, each presenting their own challenges that you have to pay particular attention to. So initially, if you're building a solution that requires custom models of any kind, where you want to teach the model about the particular kind of images that you're interested in, then you have to have a collection of images of the right kind, of showing the thing that you're interested in. And it's important that the pictures are taken in a way that is typical of the way the images will be presented in the final application. So taken with a similar kind of camera, similar lighting conditions, the object properly in view, etc. And you end up with quite a few images, so you need to have some data infrastructure to manage and coordinate the way you handle sets of images. And then you need to go through these images and mark up each image, identifying which part of the image has the detail that you want the model to understand about. You then go through a training phase where you teach the model to recognize those items in the images. And as you iterate through a number of variations of models and different versions of the data that go with it, you fairly soon have a data and model versioning challenge, and you have to be quite organized with the way you manage your data. You also have to pay attention to how accurately the model is performing on the task that you want it to learn. And you also have to think about whether there's anything in particular about the collection of images you're using that could present certain ethical issues, such as a bias towards identifying certain cases over others, fairness and privacy. These are all important, although perhaps less obvious concerns that you have to pay attention to. And finally, when your model is ready to take into production, you still have a few challenges ahead of you. You need to put together the right kind of team, cross-functional team with skills ranging from understanding about computer vision and machine learning and data management through to conventional software engineering techniques. You have to pay attention to how long it's going to take the model to process each image and what is the likely throughput of your application given the kind of demand you're expecting of it. Your model may run in the cloud, and that's commonly the applications that we work on, but there are cases that we'll talk about a bit later where sometimes you want to actually have the model calculating on a much more constrained compute device on the edge of the network, and then you have to worry about the amount of memory it will need, what processing power it will have available, etc. And then as your model is put into use and people start to use it, you may find that its performance after a time seems to be less accurate than what you expected. And that's a not uncommon phenomenon called model drift, where what has happened is the kind of inputs you're presenting to the model are no longer characterizing quite the same way as the ones that you trained it on. So it's time to retrain your model with a fresh set of images. And these are just some of the kinds of problems that you're going and challenges you're going to face as you work with computer vision models. I'll have more to say about this towards the end of the talk, but none of these are insurmountable, and we've had plenty of practice of doing these things. They're just a little bit different if your only experience is building more conventional software applications. Next image, please. So now we're going to talk through a couple of case studies. The first one I'll present is in mining, and specifically we'll be looking at what's called drill core analysis. And this is a technique used in mining and civil engineering, where engineers and geologists want to understand what the rock structure is like deep underground. Obviously, you can only see what's on the surface, but you may want to know at what depth underground does a particular kind of rock formation exist. And to determine this, basically using a special drill rig, you drill a deep hole and extract a cylindrical column of rock from that hole, and then you analyze the structure and the integrity of the rock at different depths underground. And this is used in designing tunnels and mines and building large structures like bridges and skyscrapers. This kind of analysis by geologists is time-consuming and error-prone, and would be attractive to be able to automate it. Essentially, what you have to do is take these pieces of rock that have come out of the drill hole and imagine them being reassembled into one long continuous piece of rock, and knowing at what depth each section of it was removed from underground, and then taking measurements or observations on each of the sections of rock. Next slide, please. So typically, this is what the geologist is presented with. So this is a wooden tray with sections of the rock laid out in consecutive order as they were extracted from the drill. You can see that the rock changes a bit as you go down, even a matter of a couple of meters. Some of the bits are quite clean and hold their integrity. Others are fractured into lots of pieces. There's a couple of wooden cubes there with some felt pen writing, where the person who was laying the rock in the tray has made some annotations about the depth or what happened when that piece broke off as it came out of the drill. In yellow marker pen, you can see someone has written down in meters how many meters underground this was taken. I think it's like 228 there, 229. So there's quite a range of information presented when you look at the rock in that tray. And the geologist will take a photograph of this and then analyze those photographs later. And that's a process that can take weeks to go through an entire hole that may be hundreds of meters deep. So next slide, please. So DiUS worked with a geosciences analytics consulting company named Solve Geosolutions. We worked together, the two companies, on a couple of proof of concept projects looking at what was possible to automate in this space and using computer vision, and the idea seemed to have merit. So the two companies together formed a joint venture named Datarock, and we've built a cloud platform to which mining companies can upload lots of these images of those trays, and the software will analyze the photographs and do quantitative and other kinds of analysis on the images as a service to the mining companies. And you can see here in stylized form the processing pipeline that the images go through as they're processed. There's a number of steps where you take that first photograph, you identify where are the pieces of rock in the photograph, is the box even presented correctly rotationally, or do we need to rotate it slightly? There's breaks between the rock. Where there's writing on the rock, we want to read that writing to get the numbers off it. There's a number of distinct subtasks that have to be performed, and each one is its own kind of computer vision analysis. Finally, we can create quantitative analyses on the fragmentation, the veins in the rock, the depth at which these are occurring, and put all these together into various results that can be reported back to the mining company. And the pipeline that you can see displayed here in this image is calculating something called the rock quality designation, or RQD, which is just a number that tells the geologist the degree of fragmentation or integrity of the rock at a certain depth. Next slide, please. So this is an example of the kind of output that you see from the Datarock platform. So you see the original core tray image, and overlaid on it, you can see in yellow and purple an outline of each of the major fragments of rock. Overlaid on that numbers giving dimensions of the pieces, and the information for some quantitative analysis. And so this is the kind of, is an example of the kind of processing we can do for the mining company. And When this is finished, essentially the mining company gets a result in a matter of hours that previously would have taken weeks without this computational image processing. Thank you. Next slide, please. So another application that we see for computer vision in mining is in safety. And here in this fast forward video, you can see a mining drill rig of the kind that produces these rock cores, one by one, extracting sections of pipe out of the ground in the background, flicking them out, laying them down flat, and then a robot arm picks them up and stacks them in order in a pile where another operator is operating that arm, and then they're going to extract the rock from the pipe. With people moving around with all this heavy machinery in motion, there's risk of occupational accidents and a hazard to the people. So there's a potential here to use a video camera with local image processing, watching where the people are moving in relation to the machinery while the pipe sections are being waved around, etc. And by having the computer vision computation happening in real time on site, integrated with the machinery, you can alert the operator or shut down the machinery if there's an imminent risk of a hazard to one of the people. And this requires local processing of images, and it's an example of computer vision at the edge that I'll have a bit more to say about later. Thank you. Now I'm going to hand over to my colleague Shahin to talk you through another case study. Thank you, Shahin.
Thanks, Nigel. Hi, everyone. Thanks for joining us for this talk. I am Shahin, and I'll be walking you through another use case that we specifically chose because it shows how computer vision can enhance customer user experience as well as make the life of stakeholders easier. This use case is in insurance industry, and it's an app that can be installed on the phone of the end users. It's a self-service app that is designed to be user-friendly, and it instructs the users to follow a set of procedures, and through that procedure, they can ask for an insurance for their phone. So this is interesting because it removes the need of physical appearance of the customers at centers, and therefore it is interesting and relevant to this talk as well. So through the process, the system asks the users to hold their phone in front of the mirror, and it assists them in positioning the phone properly in front of the mirror using computer vision. And when the phone is held properly, a photo is taken automatically from the front camera of the phone. It is sent to a server, and then it is processed on the server using another model. And if the phone looks healthy and there is no crack on the screen of the phone, it allows the user to ask for the insurance, the phone insurance. So this process is heavily reliant on computer vision. We are actually using two different models for this process. The first one is a phone detection model that runs on the phone. It's an edge model, and it needs to be small, and so that it can be downloaded on the phone, and it needs to run in real time on the phone. And the goal of this model is to assist the end user in positioning their phone properly in front of the mirror and to provide feedback to them so that they can do that more easily. Another model lives on Amazon SageMaker, and it's a model that looks at the photo taken from the front camera of the image and tries to classify the phone as either cracked or not cracked and healthy, so it is eligible to apply and get insurance. So let's have a look at the first model, which is the phone detection model. This model runs on the phone. It provides feedback in real time to the user, and the aim is to help the user to hold the phone properly in front of the mirror. So as you can see here, it is providing feedback to the user so that the user can hold the phone in such a way that it is placed in the middle of the gray rectangle. So if it is too far away from the mirror, it asks the user to hold the phone closer to the mirror. If it is too close, the feedback would be to hold it further away, tilt it, move it so that so that you can hold the phone in the middle of the image. After this is done, a photo is automatically taken and is sent to the server and to AWS to be processed. In terms of the technical specification of the model, it's a detection model, which means that it can localize where the phone appears in the image. And we used MobileNet version 3, which is a model that is proposed by Google late 2019. We enriched the training data using data augmentation techniques, which means you generate more images from the training data and you add them to your training data. And that way you end up having a more accurate model in the end. So this model runs on the phone. And because of that, it needs to be small. We use a technique called quantization, which means that after the model is ready, you convert any floating point number from 4 or 8 bytes to a single byte. And because of that, you lose performance of your model because of the round-off errors. The workaround is to use a technique called quantization-aware training, which means at the time of the training of the model and preparing your model, you make the model aware that it's going to be quantized, so the model won't be reliant on small precision values of the floating numbers. And that way, after you quantize your model after training, the model still, it loses some performance, but the amount of performance that you lose is much less than the amount that you would lose without using quantization-aware training. This model runs on the phone, therefore it needs to be converted into other formats. So it goes through a conversion from TensorFlow model to TensorFlow Lite. And through that process, we quantize the model, and then we convert that into TensorFlow JS. So this model works in real time. It's a very small model in the end. It's less than 1 megabyte, which means that it can easily be downloaded on the phone. And because it's a very small model, it works in real time and provides feedback to the user. The second model is a classification model that sits on Amazon SageMaker. The aim of this model is to categorize the photo or the phone in the photo as either cracked or not cracked. And we enrich the training data by adding more data through the data augmentation process very heavily for this task. And as you can see here, for data augmentation, you take an image from your training data, you apply a set of image processing transformation to that, like rotation, cropping, flipping, inversion, changing of the contrast and brightness, or adding noise to your image, or the combination of these. This way you end up having a larger training data set when you add these generated images into your training data. Also, we observed that the training data consisted of high resolution training images, but because the images it was dealing with in practice were coming from the front camera of the phone, therefore they were low resolution images. Therefore, we had to use techniques to handle the scaling and resolution difference in the prediction time. And we dealt with this problem by choosing different models that were able to handle the scaling and resolution and make the final model invariant to scaling and resolution in the end. We used fixed ResNet model, which is another model proposed in 2019 by Facebook. This model is based on ResNet 101 as the backbone, and the model size in the end was about 3.5 gigabytes. It's a huge model. And for training this model, we needed about 20 gigabytes of GPU memory, and we didn't have access to such GPUs because they are very expensive. We used 3 GPUs of 8 gigabyte memory using a technique called model parallelism, which means that you split your model into smaller parts and you assign them to different GPUs, and the GPUs interact with each other and do the computation together in such a way that you can still train your model. So this process is slower than using a single GPU, but in the end, it allows you to train a model which is larger than the GPU of a single, the memory of a single GPU. The final model was hosted on Amazon SageMaker, and through these processes and techniques, we were able to prepare a model which was near human level accurate. And in the end, we were able to categorize the images or the phones in the images as either cracked or uncracked, and therefore we would allow the user to apply for insurance. Thanks. I'll hand it back to Nigel.
Thank you, Shahin. So what's next with computer vision? We think an exciting direction for computer vision is with processing on the edge. So this is where you're doing your computer vision algorithmic processing of images on a constrained compute device because of where it's located. It's important in this case that the processing is happening right where the camera is located, and you're not communicating data across the internet to the cloud, say, where you have access to much larger computers, of course. And there's principally 2 devices that are candidates here. One is smartphones, the other is an embedded image video processor. So nowadays, people expect to interact with businesses and government through their smartphone, which includes having a camera. And we showed you in the insurance app that Shahin just presented how powerful that can be when you have computer vision working with the camera on the smartphone, interacting with the user. Altogether, you get a synergy there that's quite powerful. The other device, this embedded video processor, as I said, it's co-located with the camera typically in a particular location, and it's all about processing right there where the camera is. And so you can buy a video processor board like this one. This is the NVIDIA Jetson Nano. You can buy it for about $100. It's smaller than your wallet. It has 128 cores of GPU on board, and it can process multiple video streams in real time. So it's a very powerful, small computer at a very modest price. And this is really going to open up lots of new applications of computer vision. So really, computer vision at the moment is really waiting on people's imagination for opportunities to apply it. We've shown you a range of powerful things that can be done. For businesses, it's a relatively mature technology. There are some challenges, of course, in particular around managing data. Some people are concerned that maybe they don't have enough images to train a custom model for their application. But we've found that even with just a handful of images to get started, you can start to train a model and play with it and get a bit of experience while you acquire a few more images. Then you may be concerned about how would I turn that into a full-blown application. We have experience throughout the whole life cycle of acquiring images, training models for custom applications, and then deploying them into production as full-blown applications. So we'd love to talk with you about your ideas if you have something in mind. Yeah. thank you very much for your attention. As was mentioned, we have the opportunity to take some questions now. We'd love to speak to you further. Thank you.
Thanks, Nigel, Shahin and Mark. So we've had a couple of questions come through. The first one, why would you use quantization in the first place?
That's a very good question. So quantization is a process that allows us to shrink the model into a smaller size. And through this process, so if you don't use quantization, you need to use much smaller models. But using quantization, you can have a larger model which is more accurate or more performant, and convert that into the process, convert that into a model which is smaller in size, but it is still pretty accurate. And that's why we use this technique.
Thanks, Shahin. What are some of the challenges around productionizing ML? Don't you get everything worked out once you have a working model?
In principle, your working model is a demonstration that the idea is sound, but typically when you build a model, you do it with certain tools in an environment that's quite different from how it's going to be run if you want to build an application in production. So sometimes you have to change the language and the libraries with which it's implemented. You have to deal with issues around how fast it's going to do the inference. You have to manage the fact that the model will probably have to be updated quite regularly, more often than you would update the rest of your application. So there's many issues to be concerned with. So you need to have the model embodied in a different form of software to put it into production. And it's how you make that transition is really that step that people have to think their way through carefully. And there's evidence to suggest that around half of the models that are developed worldwide don't successfully make that step for one reason or another. Sometimes it's organizational issues, that it's one team inside an organization that builds models, but they are not responsible or empowered to put them into production. And so they have to hand over their work to another team who may not properly understand what the model's doing or even how machine learning or computer vision works. So there can be organizational barriers around that. Quite a few things have to be lined up to successfully make that transition, and that's why we call it out as a separate stage in the development process.
Great, thanks, Nigel. What are some of the ways of addressing the lack of model performance due to gaps between training data and the actual data?
So perhaps I'll let Shahin talk about that one, because that's more in the augmentation space that he was talking about.
Sure. So there are lots of different techniques that can be used, but one of the techniques is data augmentation that we showed. And what happens is that when you use that, you can deal with lack of enough data, or to make your model less variant to different parameters like scaling or different illumination and different things. So that way your model will become more accurate and more performant and more general in the end. But this is not the only technique. There are lots and lots of different ways that this can be handled depending on the situation, actually.
Thanks, Shahin. How small a data set can you use to get started with computer vision?
So when we started on the geology drill core sample work, just when we were playing around to see if we could get something to work, I think we started off initially with about half a dozen example images that we played with. We did a bit of the augmentation that Shahin described, and we started to get a feeling that this might work. And meanwhile, we were trying to get access to lots more images, but even with just a small number, you can begin to see some results that indicate whether it's promising or not.
Fantastic. Thanks, Nigel. We've got one more question, so just a reminder to throw them into Slido if you think of anything. You mentioned ML services and custom models. Why would you go with one approach over another?
So the bar to entry for an ML service is quite low. Essentially, it's a programming API, and anyone who can program in Java, Python, or JavaScript can access that API, pass an image over, and get back a data structure that tells them what's in the image. And for general purpose images of everyday objects and everyday scenery, that can be quite effective. If that's what your application needs, then you're done. That's all you need to do, and any programmer can use that. However, if you want to identify a very specific kind of image, and we had that example I gave of cyclists in racing gear on racing bikes. You know, if you want to know a specific kind of bike or specific team jersey or something like that, that is very narrowly focused, then you're going to need a custom model where you have a collection of images just of that kind of thing you're interested in. And that's when you need to go to a custom model.
Thanks, Nigel. What sources of data are used for training for more general purposes? What sources of data are used for training more general purpose models? For example, fashion.
So they would be images typically taken with a smartphone in reasonable lighting. I know people who play around with these models will sometimes go to online retail catalogs and just scrape off images that they find on the web, magazines, etc. And essentially, yeah, they're just JPEG images, and you can start to build up an image collection that way.
Fantastic, thank you. Can you combine multiple models to build a more complex solution? And if so, what are the additional challenges associated with that process?
Shahin, I'll let you take that one.
Sure. So yes, there are techniques called ensemble methods that you can combine lots and lots of different models together. And you usually end up getting much better results in the end. But the problem is that you have to host those models individually, and scaling of those models will be much harder. Also, that in terms of the infrastructure, it will be more expensive to do that. So that is something that is sometimes done in some specific models, but because the cost will increase pretty dramatically through that process, sometimes we don't recommend that.
Great, thanks, Shahin. How do you control for bias when training models in regards to diversity in a retail use case like Trendy?
That's a challenging question. I guess it definitely helps to recognize upfront that there is a risk of bias. I think we live in a biased world. That's the first thing you need to acknowledge. Our society has certain biases, and that's reflected in what we see around us. And so I think the first thing is to recognize that there is going to be some bias. And if that is a concern, because it may not be a concern in a particular situation, but if that is a concern, then I think firstly you need to try and build up a training set that has the kind of diversity that reflects the performance of the model that you want. So if you want a model that is equally likely to recognize men or women, for example, in a particular image, then what you want to train your model in is a training set that has equal representation. And if you don't have enough images of men in a particular outfit, your images are mostly of women, then probably what you would need to do is take the images of men that you do have and try and augment them with techniques such as Shahin said, so that you artificially boost the number to get equality of representation. That's probably the best way I would suggest to counter bias, but I think it is also quite an insidious problem, one that we don't fully understand yet, and is quite a challenging one, I think. Shahin, do you have further comments on that?
Sure. So, yeah, Nigel, that was actually what is happening. So the first thing is that we have to find where the biases come from and whether we can change the training data set in such a way that it is less biased. But there are cases that this is impossible, or the data set is given as is and you can't go and collect more data because, again, it becomes very expensive. And that's when you choose mathematical techniques that makes your model more fair. So there are so many different techniques, and that's one of the research areas in computer vision and machine learning these days, that you try to mathematically make your model less biased or more fair. And sometimes another approach is that you just need to remove where the bias comes from your training data. It might be a feature that talks about the ethnicity or the gender or the other aspects, and you make your model totally ignorant of that specific feature as the input. And that way you might get less biased results in the end.
Great, thank you. Are there any popular ML SaaS open source services that you suggest developers can use to develop applications without much ML knowledge?
On the landscape, the solution landscape slide that I showed, on the far left, there were ones from each of the major cloud providers, Azure, Google Cloud, and Amazon. And each of those clouds offer services. I think it's Cloud Vision API from Google. I forget the one from Microsoft, something Vision, and Amazon Recognition are the three. And they don't require you to know much at all about machine learning. Essentially, you make a call to their API, providing your image, and there's a couple of different ways you can organize that, and you get back this data structure that tells you what it found in the image. And as long as your image has everyday objects in it, and that is what you're interested in, you really don't need to understand anything more about how it works. It's just a black box.
Excellent, thanks, Nigel. Would you ever consider developing a trigger to alert the product owner that an algorithm is no longer performing to the initial specifications?
Yes, that's definitely an interesting question. The first question is, I guess, how you would even recognize that the model is not performing. That may not be easy. I'm sure it would help to have humans check that on some typical data from time to time with a human there. But yeah, I guess there probably are ways that you can do it. Shahin, do you have a comment on that one?
Yes, so you can monitor your model while it is running in practice as well through different components on the cloud, as an example, that are implemented specifically for that. And if your model drifts for any reason, which might be that the data is changing or there is something in the system that is different from the time that you trained your model, you want to be notified about that. And that's where you try to retrain your model using more collected data and the data that is more similar to your prediction. And yes, that is an iterative process that you have to do, and you always have to keep track of your models to make sure that it is working fine.
Fantastic, thank you. Do you have any tools or platforms you use to automate the ML pipeline?
Shahin?
Well, it's there are so many different aspects of a computer vision or a machine learning model. There's no specific open source tool that you use for pipelining. We have lots of different tools that they work hand in hand, and in the end you might use them because you can handle model versioning, data versioning, you can handle the monitoring of your model, but there is no real single open source or non-open source product that is definitely recommended for that.
Thanks, Shahin. A key feature of traditional stats models is explainability. What are your thoughts on the explainability of ML models and whether that might restrain adoption?
Shahin?
Sure. So that's something that we deal with a lot with, when it comes to different customers as well, depending on whether they want their model to be very accurate or they want their model to be totally explainable. There is a trade-off, because the models that are explainable are usually simpler models, and when you use them, you lose some performance. But you can move to the end of the spectrum, which is deep learning models and the models that are very complicated mathematically, and they are not easy to be interpreted, but you have a better performance. And depending on the use case, we might choose one or the other or something in between. And that's what we've seen so far with different clients as well. And it might be something that they are interested in, or it might be something that they are happy to sacrifice because they want to get a better model in the end.
Fantastic. Thanks, Shahin. What comes first in solving ML problems? Collecting the data or identifying the opportunity and then focusing on the data collection?
I think the first thing is identifying the problem you want to solve. I think if you just have data, it's quite possible that the data you've collected won't actually be suitable for solving the problem anyway. So it's much better to identify the goal you want out of it and then proceeding to access the data that you need to address that.
Fantastic. Thanks, Nigel. That looks like all the questions. So unless anyone's got anything else, thank you so much, Nigel, Shahin and Mark, and thank you to everyone for joining us and for your great questions. We'll share a link to the DiUS Slack community following this session. So if you do have any further questions, you can pop them in there and Nigel and Shahin would be more than happy to answer them for you. Excellent. So that's it. Thank you so much.
Thanks, Erin. Thanks, everyone.
Thank you.
Thanks,
everyone.
guys. Awesome.